Today we shall discuss about analog to digital converters and digital to analog converters. So, coming to the data converters, you have either to convert the continuous analog signal into the digital or the digital to analog. So, let us see the basic blocks which are required for the ADC and DAC. So, coming to the basic blocks, you have a low pass filter for anti-aliasing, then you have a sample and hold circuit, then you have your ADC, then this is your digital signal, so this will go to your DAC for digital to analog conversion. Then you have the analog signal, this is given to your low pass filter for smoothing, and this is your analog output. This is your analog input. So, now this is actually the A to D conversion, and this is actually the digital to analog conversion. So, here you can see that when an analog signal, which is actually infinite valued and continuous analog signal, is first given to the low pass filter, which is basically an anti-aliasing filter which removes the high frequency components in your input, so that the effect of aliasing is reduced. So, after that you give it in sample and hold circuit, which actually samples the analog input and holds that value, so that the ADC can convert the sample to a digital word. So actually the conversion is being done. You can see here the digital word for each analog input sample. So, coming to the DAC, this digital word is given to n-bit digital word is given to the digital to analog converter, which will give you an analog signal. Here you can see that analog signal is not exact replica of your input, it is having some high frequency components which are integrated into it. So, you need to actually smoothen it or low pass filter it. So, you send it through a low pass filter, which will smoothen or remove the high frequency components from your input and give you the analog signal, which is continuous and infinite valued. So, let us first actually discuss about the basic terms or the specifications of the analog to digital and digital to analog conversion. So, few terms. So, let us first discuss about what is LSB. So, we all know that actually the LSB in data converters is the lowest analog output which can be converted, in the sense like which is given by V reference by 2 power n. One LSB is given by V reference by 2 power n, where your V reference is the reference voltage of your data converter and n signifies the number of bits of the data converter. So, suppose if you have a reference voltage of 5 volts for your data converter and you have an let us say 3 bit DAC or ADC. So your LSB will be 0.625 volt. So you have a 0.625 steps till you get a 5 volt. So this is generally called as an LSB. Then you have the DNL, which is the differential nonlinearity. It is actually caused by the non-ideal components of analog components, which deviate the ideal and non-ideal values. Let us say that if you have an 1 by 8, 2 by 8, 3 by 8 and so on. Here you have a digital signal 00001, 0010. So this is actually the ideal step width, and so if your ideal step width is deviated, the non-ideal values of your digital word deviates from the ideal step width. So this is actually called as the difference between the ideal and non-ideal values are called as the differential nonlinearity. Next, coming to the integral nonlinearity, it is actually specified as the difference between the straight line drawn joining the output, the first and the last outputs, and the actual outputs. Let us say if you have outputs like this. So you have a deviation from the straight line which is drawn from the first output and the last output. So this deviation is actually called as an integral nonlinearity of the data converter. And you also have the signal to noise ratio, SNR, which is actually the signal, which is actually the ratio of the signal power to noise, that is at output. So normally you look for these kind of specifications in data converters. I just wanted to tell you this before going into the architectures of the data converters. And you also have the like the ADC has an analog signal which is continuous in time and infinite valued. So it has to be converted into an discrete in time and a quantized signal. So when you actually quantize the signal, you lose the accuracy of the signal with which you represent the analog signal. So when you quantize, you actually have an error called as quantization error, which is actually given by, ideally it is plus or minus half LSB. You can also give it by V input minus V step. Step is nothing but the step of your digital word to the next sample. So let us see this few architectures of the D2A and A2Ds. So coming to the DAC digital to analog conversion, the first is resistor string. So in this actually you have a string of resistors. So you have your V reference here, then you have your switches here, all are connected to your output, Okay. This is actually the simplest digital to analog converter, which basically needs an r power n minus 1 r power n. So this is R0, R1 and so on. Similarly, you have switches S0, S1, S power n minus 1. So you need an n switches and n resistors in order to design a resistor string DAC. So resistor string DAC actually it is based on the voltage division of the resistors, which are actually tapped by the switches. So whenever you have a digital input word which is given, so you have a switch which is closed, and so the particular voltage is given to the output. So this actually gives you a very good accuracy, but it depends on the tolerance of the resistors. So the disadvantage of this kind of DAC is that the output is always connected to n minus 1 switches which are off, like the output is always connected to n minus 1 switches which are off and one switch which is on. So which gives into a large parasitic capacitance at the output. So because of this large parasitic cap, the conversion, the effect of large parasitic cap, it delays the conversion of the DAC. So it slows the conversion. So the another alternative for this problem is that you can include an binary switches which allows the output to connect to n off and n on switches. So you can just actually eliminate the problem of large parasitic cap by introducing the binary switches. So let us see the second architecture, the R to R ladder DAC. So this actually uses lesser number of resistors than the resistor string DAC, in the sense that you have a V reference which is connected to R, then you have 2R, R, 2R. So a similar fashion, R, R, 2R. So this is given to your operational amplifier. D0 and so on up to dn minus 1. So actually P out, this is your feedback resistor. So here when you look towards the right of any node, the equivalent resistance you see is of 2R. So whenever the digital input word is given, it is either connected to the positive terminal or the negative terminal, depending upon whether D0 is 0 or 1. So the total voltage is actually given by I total into your RF. So your I total depends on the digital input word which you are giving to the DAC. So this I total can be given as sigma k equal to 1 to n minus 1 dk is nothing but your digital word times V reference by 2 power n minus 1 into 1 by 2r. So, these are actually the basic architectures of the DAC which are made use in ADCs for analog to digital converters. So, we will see basic 2 analog to digital converters now. The first one is flash ADC. So, this actually consists of this uses a resistor string DAC as a critical component here. Like you have a VRF as we have seen the resistor string DAC. In the similar way, you have 2 power n resistors, then you have your Vn. This is connected to your minus, your Vin is your plus of the op amp. So, Vn is to the plus of the op amp, then again you have minus here, Vn is to the plus of the op amp, then you have minus here, Vn is to the plus of the op amp. These are given to the decoder circuit 2 power n minus 1 to n decoder, and you have a denote to dn minus 1 digital word output here. So, this is actually the let us say this is I am using a thermometer code here. So, this is actually the basic flash ADC, where the Vin is compared to the voltage divided at the resistor string, and if it is greater, then the thermometer code is either 0 or 1 depending upon whether Vin is higher than Vref or lesser than Vref. So, based on that you generate an thermometer code which is given to the 2 power n minus 1 is by n decoder circuit, which decodes the thermometer code and gives you the digital output word. So, the basic problem with the flash type of ADC is the area and the power, because you need an 2 power n minus 1 comparators for an n bit ADC. Let us say if you want to design an 3 bit ADC, so you need an 7 comparators. So, if you want to increase the resolution just by 1 bit, let us say if it is an 4 bit, you need 15 comparators. So, this actually increases the area and power a lot. So, there is a main disadvantage of the flash ADC, and the advantage is that you get an output for each clock pulse. It has a high speed, in the sense like you get an output for each clock of the comparator. So, it has a high speed A to D data conversion. Okay, let us see the second type of successive approximation. In successive approximation ADC, you make use of the DAC. It is actually based on the binary search. That is, it searches for the all the quantization levels and converts to an output digital word. So, it is basically based on the binary search. So, you have an n bit shift register. So, you have a clock, let us say you have a binary search register output, then you have an SIR, then you have a DAC here. Let us say this is D0 to Dn minus 1, then you have V reference here. So, this is your V out, which is given to the operational amplifier, and this V plus has come from the sample and hold, and this is your input. So, this will go and control the So, here you can see the basic working of the successive approximation is in this way. So, actually the after sampling and holding the input value, this is compared to the output of the DAC, and the output of the operational amplifier is in turn controls the input to the DAC, means the binary search, the way it is being searched. So, let us say that the output of SAR, the Dn minus 1 is initially set to 1. So, your the output of the DAC is set to V reference by 2. So, now the V reference by 2 and V in sample is compared, and if V reference by 2 is greater than the V in, then the V out sets the Dn minus 1 to 0 and changes the DAC output to the different value. In the same way, if V reference by 2 is less than the V in, then V out sets the Dn minus 1 to it remains, the Dn minus 1 remains 1 only. So, this is actually the successive approximation ADC.